Am I audible?
Yes.
Okay, good morning, everyone. This is second lecture on radio astronomy. And in the last lecture, we focused on single dish and how and what's the kind of response a single dish produces. Today, we are going to dive deeper into it to try to understand how we can, especially using Fourier optics, understand what's the resolution of an aperture could be, and then what its gain would be. And from this, then we will try to understand a little bit more about interference, and then we'll understand how the radio interferometry functions. Right. So this is going to be very exciting. Lots of new stuff coming in. A lot of the things that you know, but we'll try to apply it in such a way that I think the overall recipe would become very, very exciting and interesting for you. So starting with the first slide here is just a quick recap of what we did yesterday, or the day before, that the quality of detection experiment using an aperture or a dipole crucially depends on two properties. One is what's the gain of the detector, because that determines how much power it will be able to collect. And this is the expression that encapsulates that, S nu being the flux density, delta nu being the bandwidth over which I am collecting the signal, and A effective is the effective area of that aperture. And we will today understand that what this actually means, why it is effective and not the geometrical aperture, why the two are different. So of course, like I would like to have as much large collecting area as possible, because that's what would allow me to collect more and more power from the source of interest as possible. So if you look at this cartoon here, an aperture would have a main lobe, main beam, and then it would also have secondary lobes, which are seen here. So it will also be able to pick up some signal from here. So the challenge for my experiment is to design the antenna such that I receive signal from my source of interest in the main lobe, but whereas in the secondary beam, I do not pick up any stray signals. That is the first thing that I should try to do, because any stray signal that is coming into my through the side lobes would actually affect my measurement, and it would also increase the system temperature of my system. And if you would recall from the last lecture, this means that the noise in my measurement will increase, so the precision will go down. So what we need is a very good main beam efficiency. Now, second thing is the directivity. In this, I want to localize the source of emission. So if, let's say, I point my telescope towards two sources A and B, which are there in my beam, I should be able to tell like them distinctly that how much emission or power I'm receiving from each one of them. And just a simple dipole on its own does not provide these properties adequately. So we need to do something more to build telescopes which can provide us desirable properties so that we can do meaningful astronomy. And the most commonly used setup that you would come across is that there is a feed or a dipole which is used in combination with a parabolic reflector, as shown here on the left. So what is done in this case is that this reflector simply acts as a large collecting surface, which is shaped such that it converts the plane wavefront, which is incident here, onto the reflector, and then it is converted into a spherical wavefront, and then it gets sort of collected at the focus here, which is where I can place my dipole or horn feed or any detector that I would like to have. So this incoming wavefront is then incident on the parabolic dish, is then collected at the focus, and then detected by means of this dipole here. So the response at the focus now is a result of coherent phase summation of the electric field that is happening here, because you can see that the path length from any point on this aperture to the focus is actually same. That's pretty much the geometric definition of the focus. And any wavefront that is coming off axis, like from any other direction, in this case, in this cartoon, we have only shown the wavefront which is coming right from the top. But if there is any off axis incoming wavefront, they may add constructively or deconstructively across the aperture. And at the focus, the detector would just be a simple dipole or a Hall antenna in this case, where I'm collecting this signal. So what advantage do I get from this? So this dish gives the advantage of having a directional gain, which comes directly from the resolution being proportional to lambda by d, right? Lambda here is the wavelength at which I'm carrying out the observation, and d is the aperture of the dish or the diameter of the dish, as shown here. And we will see why this is lambda by d. From where do we get this? But a simple conclusion of this is that if I want to have a good directivity and also good collecting area, then I should try to make large dishes, large apertures as much as possible. And there have been many such large telescopes built over last many decades. So starting with, we have Parkes telescope in Australia. It has a diameter of 64 meters. This is huge. I do not know whether any of you have actually gone close to something which is a telescope which is like 30-40 meters even. So 64 meters, you will find that if you ever get a chance, it is huge. And this is a Green Bank telescope in West Virginia, USA, and this is 100-meter diameter. And this is the largest steerable dish or the single dish telescope that we have. But there are bigger single dish telescopes also. For example, this is Arecibo telescope in Puerto Rico, and this has a diameter of 300 meter. And there's also now already functioning 500-meter aperture spherical telescope called FAST. It is in China, right? So as you can see, like up to 100 meter, we have dishes which are actually steerable. But as we try to make larger dishes, it becomes practically difficult to make them such that we can steer them. So we have to start making apertures such that they are made up of panels which are fixed on ground, and then sources which are transiting across the zenith, then they are observed. But still, the collecting area that we get out of it is huge. So it's still a lot of progress in terms of the sensitivity. But increasingly, it becomes more and more difficult to make larger dishes. So the problem that we face after this is that what is it that we should do to get even more resolution and even more collecting area if we want to make progress. And I will try to give you some examples later in the lecture to demonstrate that why the resolution that we get out of these dishes is not adequate. Why should we strive to get even higher spatial resolution and more collecting area? So before going into those precise examples, let's try to understand how we can understand what's the response of an aperture would be. So in last few slides using ray optics, we appreciated the fundamental role of a parabolic reflector, right? Where we could see that like, okay, an incident wavefront gets focused and all the power gets collected there and we can detect it easily. But if you want to investigate this more, to understand what's the actual quality of the image will be or what's the resolution that is provided by the aperture, then we will need to go into Fourier optics. And the basic idea in Fourier optics is that an advancing wavefront or a plane wavefront, if I take, as it is intercepted by an aperture, now every point on the wavefront will be regarded as a source of secondary wavelets. And this is an idea which you must have come across when you have tried to understand diffraction or interference across different apertures. So due to diffraction, especially you find that this wavefront is able to then spread into regions that would otherwise be unlimited if you are just visualizing this problem using ray optics. And what happens due to the diffraction, that on the screen, you would find that it's not just uniformly illuminated something, you find fringes that, or some places there is constructive interference and there some places there is destructive interference. And it is this interaction between the incident wave and the aperture that determines the resolution of optical devices and also the quality of the image, like how good the image will be. Whether if I put a point source through the aperture, it will look like a point source. Whether it will look like something else, this is what determines. And when we view this assembly like this, we can actually show that the far field or the Fraunhofer diffraction pattern that we get from an aperture is actually the Fourier transform of the field across this aperture which is causing the diffraction. So let's try to do that. Perhaps some of you have already done it in your wave optics courses, but let's try to recapitulate some of it. So what we are trying to show in this slide is that we want to consider an aperture with a constant extent. This is x-axis and vertical axis is the z-axis. And we have y-axis which is going into this slide. And we have an aperture which is of length a along the y-axis. And what we want to do in this case is to determine what would be the field at point P, right? So we can write in field due to an infinitesimal element dx like this. And if I want to have determine the field due to the entire aperture, then I'm just going to integrate over uh, this entire aperture, and I will get this simple expression. And if I substitute here these two following things, one is that r is approximately equals to r plus x sine theta. This you can work out very simply. R is this distance here from P, actually this one here, and then theta is this angle. And then also I substitute for x by lambda. That is, I am going to measure my distance in the units of wavelength. And that is something we will do throughout all the applications that we will do here, that we will be measuring distance or separation in the units of wavelength at which I am observing. So when I do this substitution and carry out this integration, I get this simple expression here, where this quantity Ex lambda is defined like this. Yeah, right. And as you can recall, that this is nothing but a very simple Fourier transform relation that we use in various branches of physics. And so what is Fourier transform? Just look at it in a couple of slides in case some of you are not familiar with it. So in general sense, when we start learning Fourier transform, they are generally motivated using like as an extension of Fourier series. What is shown here is that if I have a square wave, I can actually represent it by a summation of a number of sines and cosines. So this is a basic idea of Fourier series, that complicated periodic functions can be written as sum of simple sines and cosines, right? Weighted sums of sines and cosines. And Fourier transform is just an extension of this, where the period of the represented function is stretched to approach infinity. And that's what gives me this expression here at the top. These are the expressions which you would have seen in your textbooks. So this is relating two domains S and X, which in some cases could be, for example, time and frequency. If you're doing signal processing, it could be also like used in, would have come across in quantum mechanics also. So this is how the forward Fourier transform will be related, and this is how the reverse Fourier transform will be related, right? So these are the expressions that we are going to use in next few slides to understand how the response of different apertures are going to be for an incident source. So let us take a very simple case of an uniformly illuminated aperture, right? That's the case we were trying to understand. Just think of it like a single slit or something where it's uniformly illuminated here like E naught, and D is the size of the slit. So so anything outside this, the response is 0. So what I need to do, I just take this first Fourier transform expression, I substitute this function here, and if I do this simple mathematics, I come across that the Fourier transform turns out to be E naught, and this function here, sine pi ds over pi s. This is nothing but the sinc function. And on the cartoon here, you can see that this is the box function. This represents my initial uniformly illuminated aperture, and its Fourier transform is a sinc function which looks like this. And in curves in light, you can see what happens if I actually choose a broader box function, then the corresponding response of the sinc function will be narrower, right? And this is also something which you would have also come across in basic Fourier transform properties. Trying to understand these basic Fourier transform properties, and along with some basic relations between some simple Fourier transform pairs is really very, very important if we want to understand optics and how imaging takes place in radio astronomy or any field of astronomy. So I have summarized some of these Fourier transform pairs here. For example, a constant function is a delta function. Box function we have seen is related to a sinc function. Then if you take the triangle function here, it would be a sinc square. And a Gaussian Fourier transform is a Gaussian. But here also, again, you can see that like a broader Gaussian in one domain will correspond to a narrower one in the other domain. And then we have step function and some of the other functions like sine function and cosine function, which would be related to a pair of delta functions in this case. So in case you are not familiar with some of these, all of these can be derived using very simple mathematics. You can go through it and finish it in a couple of hours. I will request you to go do that. And also at the same time, try to memorize some of them, because these becomes then very quick look things for you to very quickly understand like what the response would be in a particular situation of an aperture. And these are some very simple theorems of Fourier transform. That's also, I think, very useful to understand. First one is just the linearity, which tells that if we add two functions, then the Fourier transform of the resulting function is simply the sum of the individual transforms. Then next one is the similarity, that for a function fx here, if I multiply, if the x-axis is scaled by a constant a, so that I get f of ax, then the corresponding Fourier transform is like this. This is what we were using to tell or understand that a broader function in one domain will correspond to a narrower function in the other domain. Then we have shift or translation in one domain, which corresponds to multiplication by an exponential base term in the other domain. And then something very important comes here, which requires a little bit more thinking. So after the lecture, probably you should go offline and think a bit more about it, and that is the convolution. And I'm putting more emphasis on this because this is a very, very important operation in astronomy and data processing. So if you're doing any operation on the data, whether you're trying to smooth the data or whether you're trying to do some imaging, convolution plays a very important role in that case. So this is so what is the convolution theorem telling? That if f and g are two functions, and this star between them represents the convolution of these two f and g, and this convolution function is written like this. This is the last line in this slide. Then the Fourier transform of this convolution is actually the product of the Fourier transforms, right? This is really very important to understand and to also then remember it. And let's try to understand some of these properties using some very basic examples that we're already familiar with, but we have looked at them slightly differently, right? So let's look at this convolution, what it means here. So on left hand side, let's look at just the first panel. What is this? This is just a simple delta function, two delta function, a pair of delta functions at minus t naught and plus t naught, right? And what will be their Fourier transform? This is this cosine function. So if I go back just to show you here that this is what we are doing here, right? This is the last one, that is the property that we're using here. So I know that its Fourier transform will be this. So now what I want to do is to just recall that what would happen if I had two slits actually, right? If my aperture is nothing but two slits, then you know that this Fourier transform here or the fringe pattern is like a cosine there in that case. Now next what I want to do is to represent it with slits of finite width. So how I can do that? What I can do is that I can convolve these two delta functions with a box function. Convolution here will mean that I will get a box function at the location of minus t naught and another box function at t naught, because convolution is nothing but shift and multiply. So what I'm doing is that I have taken this first function, which is the pair of delta functions, and I've taken this box function and I'm shifting it across t axis and I'm multiplying it. So you can see that wherever the box function is non-zero and centered a delta function, I'll get a non-zero value, and then it becomes zero again. Then I get another delta function here, right? So now if I take this box function, I know that its Fourier transform is a sinc function. That is something we worked out a few slides ago. And then I just want to ask the question that what would be now the Fourier transform of these two box functions, or in other words, slits of finite width, which is what I'm interested in. I want to know what the response will be. And in this case, I know from Fourier convolution theorem that these would be nothing but the multiplication of the Fourier transform. So if I take this cosine and I take sinc, and then it's just the point by point multiplication of these two, and I get what? A cosine which is multiplied by a sinc function. So if you recall your realistic Young's double slit experiment, that's the kind of response you get on screen, which is you have a sinc function which is sitting on top of your cosine fringes, right? So this is an alternative way of understanding a lot of optics experiments, and it becomes a lot more fun to also view Fourier transforms in this way. So now I'm just showing exactly same thing in a slightly different way, something which is probably you are more familiar with. So this is now my double slit experiment, a plane wavefront incident on it. I generate another, and this is the width A here in this case, finite width. And then on the slit, I'm trying to, on the screen, I want to understand what kind of fringes I would see, right? So if I just had one slit, then I would have this sinc function sitting here, right? So now I open another slit, initially, let's say it was covered, but then and they don't have a width in this case, idealized function, then I will have this interference pattern, which is the cosine function. And now if you put both the things together, which we did in the second case here, or the previous slide, then I have this cosine, which is now multiplied by a sinc function. And what we are interested in here is in the intensity, then I take a square of this, right? So this is a very simple way of using Fourier transform to understand what the response of a double slit experiment will be. Cool. So now let's apply to some of the cases in astronomy here. And we cannot apply to many cases, but whatever we are going to discuss here will be applicable to apertures of many different types. For example, like you can pick a rectangular aperture also, and a lot of what we discussed today will be applicable to that as well. So now what we are doing here is that we are going to replace slit with a circular aperture, because that's what we deal in our real life experiments, which is like two-dimensional apertures. So in this case, if you work out, and again, like this is something very easy to work out, you can just represent this circular aperture in polar coordinates and carry out the two-dimensional Fourier transform, and you would find that its Fourier transform is actually something which looks like sinc, but it's not really sinc. What it is exactly, it's actually a Bessel's function of first order, right? That's what it is, and this is what it looks like here. And you must be familiar with this name called Airy's disk. This is a mathematical representation of Airy's disk, and half power beamwidth of this function is 1.02 lambda by d. Okay, by half power beamwidth we mean that, like, if I take the peak response and I go to a point where the power would falls to half, then that separation is 1.02 lambda by d. And the first nulls, if I take, they would be separated by 1.22 lambda by d. So you can already see that this lambda by d coming into picture, and that's where we get a relationship with the resolution here. In this, if you see, so first thing that we need to understand, that if I just have a single object, right, which is on the left, if you see, then there's a single object. If I make an image with a circular aperture, it will not look like a simple Gaussian broadened by something, or not like a box function. It will actually look like a sinc function here, as you can see. Here in solid and dashed lines, we have compared what the response will be if I compare a circular aperture with a box aperture. So you can see that, like, the width of them can be slightly different, and the side lobes also are of different level. So the choice of aperture, or the type of how do I design my antenna or a telescope, with crucially depends on, like, what kind of resolution I want for, and what kind of side lobes are desirable for my experiment. And of course, ideally we will say that, okay, give me a telescope which has almost zero side lobes and has infinite resolution. But of course, in practice, that is not possible. So a lot of trade-offs come into play, and we will consider some of them. But before going into that, what happens if if through my aperture I am seeing actually two objects? So in that case, I can tell whether these are two distinct objects or same objects. That will depend on the resolution of the instrument, and that is defined. I can define by using what is called Rayleigh's criteria here. What is Rayleigh's criteria? Rayleigh's criteria is actually telling me that if there are two nearby stars or objects, they will be resolved if null of the one falls on the peak of the second. So in this case, the separation will be 1.22 lambda by d, right? So that's how we get this 1.22 lambda by d into picture here. And that's why a few slides ago I was saying that, okay, the resolution of my aperture is proportional to lambda by d. And this factor 1.22 here can change actually depending on what type of aperture I'm using and how it is illuminated. All those things will determine what the resolution of my instrument is, right? So now let's just try to put all of these things together. So if I have a telescope and I want to observe something, I want to know two things straight away. What is the resolution and what is the collecting area? Because collecting area will tell me the sensitivity, the precision with which I can make measurement, and resolution will tell me that the kind of details I can pick up from my observation. So resolution is 1.22 lambda by d we have seen. And for collecting area, I can very simply say that, okay, I'm going to collect the geometric area here, which for this aperture will be pi by 4 d square is simple. But both these things are true only if the dish is uniformly illuminated. What do we mean by complete illumination in this case? Is that my feed at the focus is placed such that it is actually collecting radiation from the entire dish, entire aperture. But it may not do so. And you would say that, okay, why would I want to have such a feed which is not collecting radiation from my aperture completely? And you will be surprised to know that this is something which is done by design. It's not something which is an unintended or side effect of design. So, but straight away, what happens that as a result of this incomplete elimination, don't have geometric area as my measure of collecting area, but I do have what is called as effective area. And the ratio of these two is called the aperture efficiency. So this is going to be always less than 1. And in ideal case, it can be close to 1. So now let us try to understand some of the situation. First is the desirable situation, that why I would want to have an effective area which is less than geometric area, that is when the dish is not uniformly illuminated. Because if you think of a feed which is now looking at this dish completely, there are two things that can happen. One is that it may also start picking signals from the ground. Because let's say if this is a parabolic reflector which is looking upwards, and now there is a feed sitting here which is pointing downwards, whose power pattern is pointing downwards, then at least the south lobes will actually be pointing towards the ground, and you will start picking some spillover radiation, and that will increase your system temperature and reduce performance of your instrument. And second thing, we know, if you go back to my Fourier transforms here, that wherever I am coming across sharp edges here, like I end up with a function which has these ringing, right? If I take something like a nice Gaussian, it falls off nicely in the other domain also. But whenever I have these sharp edges like a box function, especially for example, I end up with these corresponding Fourier transform here, which has got these side lobes and ringing. So that is something which I do not want my instrument to have. Have these big side lobes, right? I want to have my response to be such that it comes nicely, and the side lobes, I know that they cannot go to 0 because my aperture will always be finite, but they should be as less as possible. So what I can do is that I can take a box function or a circular aperture here, but I can multiply it by a certain grading function here, which means that I can taper its edges here, and that would give rise to a Fourier transform which is much smoother in the other domain, right? So that's the kind of thing I would want. So, and that is something to reduce the side lobes, right? So this is the first situation where I would want to reduce the illumination of my disk. And then there can be some challenges that come from the engineering of a dish. There are two things that we assume that, okay, my dish is a perfect reflector, but it need not be. It will have some imperfections, because especially if you are looking at very large dishes, especially if you're looking at like tens of meter or 100 or 200-meter dishes, you don't make them as a single entity. You make panels of different shapes and you combine them, you stitch them together or join them together to realize a parabolic reflector. That's how you get a parabolic reflector in practice. And it may not be then an ideal shape. And also, like when the dish is so heavy and you start observing with it by steering it from one direction to another, then its shape may start getting distorted. So what this will mean is that at the focal point where you have put your feet, it may not actually be like, everything may not be actually coming perfectly in focus. That is, coherence will be reduced there. And also there can be other imperfections in the dish as well. And if those of you who are more interested in understanding it more, the basic tools of Fourier transform that we have discussed today, you can use them and try to understand what is Roux's formula. And that tries to encapsulate how the response at the focus of a dish will change due to various imperfections across the dish. Today we are not going to cover that. Maybe some other day. And second thing, like the moment I put something at the focus here, a feed here, it blocks the aperture, right? The wavefront which is coming from top is actually, a part of it actually is going to be blocked here by this feed. So what this would mean, this would result in what is called an obscured Airy pattern, right? This may sound something very confusing as such, but if I again go back to my Fourier transform properties here, what is it? It's very easy to guess. So what I'm having, I have a box function here, let's say, starting simply, that I have got to represent my aperture. And then I have some another box function which is representing my dish, right? And it is a much smaller one because my, let's say that my feed is much smaller. Of course, that is practically true also. So what I'm doing here through aperture blockage is that I'm actually subtracting these two functions, right? And this, so I can use the linearity of Fourier transform property here, uh, and I can take the Fourier transform of these two functions, I subtract them and I square them. Then I would, what I would get an obscured Aries pattern, right? That's what, so it's very easy to obtain it mathematically, but also if you are able to understand or and remember some of these basic Fourier transform theorems and properties, you can very clearly visualize that what would be the output of such a feed blockage or from the obscuration. There are two simple things that are going to happen. One is that my central maximum or the response uh, in the main lobe will go down, and second thing is that my side lobes will increase because of this blockage, right? So these are various considerations that we have to, or engineers have to take into account when they try to make very good dishes. So from what we considered here in this slide, it may seem like, okay, it is all a mess, but it is not the case. It is possible to design dishes which are very good. They approach very close to, they have very good efficiency. They also have very good coherence across the aperture as well. But it requires, all this requires very good engineering. It is not something which can be done without understanding the details of various things that we have been considering here. So I'm showing here an example of MeerKAT antenna. And you can see, I picked up this particular example here because you can see here that instead of having this feed at the prime focus, which is what in some of the various other examples we have seen, the feed is actually has been offset. And this configuration is called offset Gregorian. And so feed is, so there's a reflector here, and all the feeds are placed here, in this case below it. And you can see that this has been done to reduce the blockage of the dish. And why this has been done? Because this has been done to achieve very good imaging properties with the telescope. And this is not a theoretical example. This is a telescope which is now just becoming functional in South Africa. It is the most sensitive radio telescope at centimeter wavelengths. I will talk a little bit more about in tomorrow's lecture when we will also discuss interferometer array. But this is one very good example to understand like how to design a good dish, where you can see that like feed is and everything else is not at the prime focus, but it has been offset to actually reduce the aperture blockage. So next, we want to understand how the interferometry functions. But before that, what is the need of interferometry? You can very well say that like, okay, I have these single dish instruments which I can make, and then I can actually make them as large, and I don't care if they are fixed to the ground. I can get 300 meter, 500 meter. Wouldn't that be enough for my requirements of astronomy? But that is not the case, because tomorrow when we will discuss a little more science that is to be done with square kilometer array, which is not even built, you would find that even higher resolution and sensitivity are required to do competitive astronomy, especially now. So this is one example, and this is all this astronomers like amateur, professional, or even anybody who is interested in looking at the skies, familiar with Orion constellation, and if they have stared a little bit more, they would also know what the Orion nebula is and how it looks like, right? So if I have an instrument and a telescope, I say that, okay, I want to make an image of this nebula, then I have a single dish, then I can point it towards this and say that, okay, and I can start mapping it like, so each circle here represents a kind of a beam of the telescope, and I can start mapping this Orion nebula like this. But the question to ask is that what is the resolution that I am obtaining from these observations? So angular size of the Orion nebula is about 1 degree. So this is twice the size of moon, right? So it's quite big. So if I take GMRT, Giant Microwave Radio Telescope near Pune, and it is built up of 45-meter dishes. So now we know that if 1.4 gigahertz frequency, which corresponds to 21 centimeter in wavelength, I get do lambda by d being 45-meter here, the resolution that I get is approximately 0.3 degrees. So this is 1.2 lambda by d, that's what I have done, right? So you can see that, like, if I take this Orion Nebula, which is looking has so much detail here, and if I just take a GMRT dish is 45-meter, and it's not a small dish, it's a big dish, like the largest steerable dish is 100-meter. So with that, you would get like factor of 2 better resolution. You can see that, like, you are not going to get much science done with that, because the level of details that you will pick up will be spread average over such a large area in that case. And this image is actually coming from Hubble Space Telescope, which has sub-arc second resolution. So one important aspect of astronomy is to observe any object at multiple wavelengths, because these multiple wavelengths bring information about different physical processes, and then we measure different physical quantities from them and combine them, and through them then we can understand what's actually going on in that place, or how the evolution of that particular object will take place, right? But let's say if I at one wavelength I have such a detailed map, and another wavelength radio in this case I make such a lousy map, then I cannot really combine those measurements. So if you want to do meaningful astronomy, you want to have be able to achieve similar resolutions at different wavelengths, right? So the challenge here is that we want to go from 0.3 degrees to not 0.1 or 0.01 degrees. We want to get to sub-arc second resolution, because that's what this kind of image is having, and other wavelengths are able to achieve. So the answer to that is that, of course not, we cannot make a dish now which is 5,000 meter. It is the answer lies in radio interferometry. And why is that? And that is something we are going to now understand in rest of the lecture today. Okay. So radio interferometry, what we are going to, so this is the conclusion that we will reach after a few slides from now, which is that in radio interferometry, what we try to do is that we take large number of small dishes. In case of GMRT, it is 40-meter size dishes, and we synthesize a continuous aperture, which is much larger than this. And in case of GMRT, we synthesize an aperture which is as large as 25 kilometers, right? So we are making a dish virtually, which is 25 kilometers diameter, using dishes which are only 45 meter in diameter. Now, root of all the interferometry in astronomy lies in Michelson's interferometer, but there are some differences, and it's very useful to appreciate what are those differences. So Michelson's interferometer, or this experiment, it was carried out at Mount Wilson Observatory, and what it did was it measured the size of Betelgeuse star, and that was cutting edge astronomy at that time. And it had baselines. Baselines is actually the separation between the two antennas in an interferometer, or two mirrors in this case. We used the term baseline for that. And in this case, fringes were actually, or the interference pattern in this case was observed by eye. So this setup, I'm sure you are very much familiar with. There are these two mirrors. One of them is fixed, one of them is movable, and there is a source here. In case of Michelson interferometer, it is a star here, and then this incident beam is split into two parts, and as I move, and then interference pattern is produced here on the screen, in case, or a detector, and then this, as I move this mirror, the interference pattern actually changes, and from this then I can determine what will be the size of the source. And how is that? That's something we are going to see, but this is pretty much the essence of Michelson's interferometer. And if there's another source which is an off-axis location, what would happen in that case? I know from my simple Fourier transform now is that I would see here just the superposition of the two fringes on my screen. And if I want to write it with some very simple mathematics, I can say it like if 1 and 2 are E1 and E2 are corresponding to my two sources, and this is what I will see on screen: E1 plus E2, E1 star plus E2 star. These are complex conjugates here. And if I carry out this simple algebra, I would find that this actually, if I take an average over some time, it actually approaches to 0. Why is that? Because these two sources are mutually incoherent in this case. They have nothing to do with each other, right? So there are no fringes that I would see. And that's something we know from Young's double slit experiment also, right? But let's say if I consider a slightly different setup where now there is a single source, and I actually am looking at I'm receiving radiations from two different paths. One is this path, another is this represented by the dashed line. And in that case, of course, they will have a constant phase difference between them because they're coming from the same source. And in that case, actually, I would be seeing an interference here, right? So now what happens that if I have two sources, and when I say two sources, they would of course be incoherent because they are not related to each other. And that is something happens to any extended source that we see in astronomy also, that we can think of this extended source in the sky being made up of a large number of, or being an ensemble of large number of sources which are actually emitting independently or incoherently in this case. So if I have two such sources and they're eliminating two slits A and B, then I can write the expression which I wrote previously in this case like this, and I will end up with three types of terms. One is that there will be these constant terms here which were corresponding to these, so they don't contain anything meaningful in this context here. And then I would also have these terms which are corresponding to incoherent. They will be approaching to zero. Okay, in the last row here is a mistake. This will not be approaching zero. Of course, this is what I am interested in here. So what I would get in the end is the sum of the fringe patterns from the two sources in the end in this case, right? So what I am getting here through this is actually a visibility or the fringe pattern which is actually reduced. Its sharpness is reduced. Why is that? Because if I started with a fringe pattern and then I have another source involved here, then its fringe pattern would not be exactly coincident with that. It would be slightly shifted with respect to that. So fringe patterns will begin to wash out. And that is something Michelson actually quantified this using this quantity called visibility, V. And this is I max, I mean, I max plus I mean. So fringe visibility defined like this is equal to 1 when the source is unresolved, right? Because then I see it as just one source. And as I increase my baseline, the reduction in the visibility then becomes the measure of the source extent. Okay, in that case. So this is what we are looking at here is an addition interferometer, and I will summarize it very quickly in my next slide. But this was something which was implemented for the first time in radio interferometry as well. And this is a C-cliff radio interferometer here. What was done in case of C-cliff radio interferometer, that this telescope here was set up such that if a source is close to the horizon, then you would receive a part of light which is or waves directly to the telescope, and another part will actually be reflected from the surface of the sea. So a geometry like this which we saw in the previous slide, and that is what we would get. And then interference pattern that is generated out of this in this case is actually was used to study some of the radio objects in the sky and to measure their sizes. So this was some of the very first earliest radio interferometry experiments in the But when we talk about radio telescopes here, or the modern radio telescopes, we do not actually do addition interferometry. What we do is use is actually a multiplication interferometer. And that is something which is not possible in optical domain, but it's very much possible in radio domain, because using our dishes and feeds, we can actually directly measure the coherency or sample the electric field in the aperture. So how do we do that? So I can, in this case, directly measure. I have lost my cursor. Yeah. So even E2 star here is my coherency that I'm measuring. And if V1 and V2 are the voltages received at each of these two dishes here in this case, and I'm pointing it towards a source which is at an angle theta with respect to the zenith, then at V1, the voltage is A1 cos 2 pi nu t, and at V2, or the other dish, I would see it is after certain delay, right? This is nothing but just a geometric delay. And you can work out that this geometric delay is nothing but it is actually B sine theta over C here, okay? And if I take the product of these, the voltage here, then it turns out and integrate over a certain time, then I get cos 2 pi nu tau g. So this is my visibility or the fringe, right? So in this case, multiplication, what is the first advantage that I'm seeing here? Since I'm doing a direct multiplication, I'm only picking signal which is actually I'm actually rejecting any signal which is common to the antenna. So my noise signal is much more cleaner in this case. I don't have noise biases coming from these terms like A1 square plus A2 square, which was sitting in the case of addition interferometer, right? So that's the first thing that one is able to do. And another thing you can see is that the phase that term, this tau pi nu tau g, is actually very sensitively dependent on the position of the source in the sky. That is theta. As the theta changes, this phi will also change, d theta over d phi. So you can work this out for a simple example. You can take this expression, estimate what d theta by d phi will be, and using that, then you can calculate that for a certain, if let's say if a source moves by let's say 1 arc second, what would be the corresponding change in the phase d phi for that. So now recall for what we did for single dish, right? We got this Bessel function there as a response of it, and the resolution for that was dependent on this capital D, which was the diameter of the dish. But if you look at this expression at the top here, in this case, actually, I am having a dependency not on capital D, but it is dependent on B, which is the separation between these two dishes. So very quickly, I'm coming to a situation where my resolution of the instrument is dependent not on the diameter of the dish that I'm using it to build it, but is actually coming to depend on the separation between the two dishes, the baseline. But field of view still corresponds to the capital D, right? And you can also visualize it very cleverly using using analogies with Young's double slit experiment that we did, right? You can think of these two dishes as just two slits, and you can then try to understand what the response will be and how it will get modified if I change separation between the two slits or two apertures in this case. So this is how like the generality of Fourier transforms comes into play to understand things across various domains. But to formally understand it, we need to go through rigorously Van-Sittard-Zernike theorem. And that is something you can find in almost every optics book. And I would recommend like you try to look into in some of the standard optics book like Born and Wolf. And there are some very nice applications of that also. But very briefly to cover in this lecture, what it tells that if I have an extended quasi-monochromatic source, and it's incoherent, which means that like different points of this source are emitting independently of each other, then the field at points P1 and P2 on the ground, if I can write it like this as E1 and E2, and if I then take a complex correlation of these, which is E1 star, and then I take average over time, then I come across this very simple expression here, which is at the bottom of this slide, that V12 as a function of u and v. U and v is nothing but the separation between these 2 points measured not in x and y, but in the units of wavelength. And as I was describing before also, that it is really useful to measure the separations in the units of wavelength here. And this is then equal to ILM, which is the intensity distribution in the sky, and this exponential. So this is nothing but a simple 2-dimensional Fourier transform expression here, right, with some approximations. So what this Van-Sittard-Zernike theorem tells, that visibility, or the coherency function that I sample in this UV plane, we call it UV plane in radio astronomy, after these coordinates that I'm using here, is a Fourier transform of the intensity distribution. So what my problem is reduced to now, that somehow if I can measure this UV on the ground, then I take an inverse Fourier transform of this, then I will get the image in the sky. Of course, there are a lot of things that we have to do in between. What is that in between, we will do tomorrow, but we will just try to understand that what it means in a simple sense, like if I have got ideal visibilities, how to get an image out of it. So first thing is that when we consider this simple 2-element interferometer, we just multiplied the two voltages and got this cosine term, right? But visibility that we are getting here is a complex visibility. That is, we have both amplitude and phase. So how it is achieved in radio interferometry, that one implements what is called complex correlator, right? What happens that in addition to taking this simple multiplication, it also does another multiplication where in the path of one of the signals, we introduce 90-degree phase difference. So I get another measurement, which is sine 2 pi nu tau g here, right? So I have this V12 cosine and V12 sine here. And complex visibility now is just the sum of these two. V is equals to V12 cosine plus V12 sine. And the amplitude and phase of this visibility can be defined like this. And I can also write this visibility simply as A times exponential of iota phi. So that's how my complex visibility is defined. And that's how we make a measurement using a two-element interferometer or radio telescope in general. Right. So what about the negative frequency? That's another thing, because whenever we write actually a Fourier transform, we integrate it from minus infinity to plus infinity like that, right? So what happens to the negative frequencies? So we discussed a lot of Fourier transform properties, but another thing is that you can very quickly infer that image that I make is always going to be real, right? Sky is real. There's nothing imaginary about it. Everything that we have in nature is real stuff. So what this implies is that if this is how they are related, intensity and visibility. So the corresponding function in the conjugate domain is going to be Hermitian. What is meant by Hermitian? Hermitian means that the real part of that function is even and imaginary part of this function is odd. And you can see this through this cartoon also. But what this means is that f of x is equal to complex conjugate of f and minus x. So which means that we can, although we are measuring only half of the UV plane, we can fill the other half with complex conjugates using this VUV is equals to V complex conjugate minus U minus V. So this is how I can fill my entire UV plane. So this is, so now we are in a situation to understand that when we were day before in the previous lecture looking at GMRT telescope, we were seeing, okay, there are all these dishes which are small 45-meter diameter, but they have been put in a certain fashion, right? So why they have been put in this fashion? Because my two-element interferometer, what it is doing at any instance, it is measuring one Fourier component corresponding to the intensity distribution in the sky. Just one Fourier component, right? But if I want to make a sensible image of the sky, then I must obtain as many Fourier components as possible. How do I do that? I must have many dishes then, because at any given instance, they will be then measuring multiple Fourier components. That's first thing I would do. And then, of course, I know that the resolution is going to come from the longest baseline and not the diameter of the dish. So what I can do is that I can try to put them as far as my science requires, as far as the situation allows me to do. So in case of GMRT, the telescopes were put like 25 kilometers apart. So what this means is that at the same 1.4 gigahertz, if I estimate what the resolution will be, it's now 3 arc seconds, not 0.3 degree, right? So this is something which we have now achieved through radio interferometry. Otherwise, it would not have been possible at all. And second thing that one can do is that instead of just observing this source for a particular instance, we can track it as it moves across the sky as the Earth rotates. Because then what happens, that if I look at this geometry back, this projected baseline between any two dishes is going to change. It's B sine theta, right? This theta is going to change. So although the physical separation remains same, their projected baseline is going to change. And because of that, the same pair of antennas would actually, as I track objects in the sky, would be actually sampling the different Fourier component out of it. And I can do something more clever depending on how much money I have. I can start putting dishes on rail tracks. So depending on what my object is, how I want to image it, I can then move those antennas either close by. If these antennas are close by, then I will be sampling Fourier components corresponding to the extended structures in the sky. That would give me a certain kind of a measurement. And or if I want to see only the details out of it, then I can move them very far apart. Or if I want both of them together, then I can come to a compromise where I can put some antennas really close by and some antennas far apart, so that I measure both the types of Fourier components. So again, going back to GMRT, would find, if you look at it in detail, you will find that of its 30 antennas, 14 have been put within 1 kilometer. So they are sampling large scale distribution. And then remaining 14 actually have been spread out randomly over an area of 25 kilometers. Because then I am actually measuring as many non-redundant baselines as possible. So that's the essence of it. And since I gave you an example of very large array in USA, this is how some of the UV plane distributions will look like. So in these plots, what is shown here is that one is using VLA to look at a certain object in the sky. So each panel is showing a declination of the object here. And each point in this figure is actually representing where the measurement has been made. It's not actually the measurement itself, but the point where the measurement has been made. And we will call this a sampling function, and something which we will talk about a lot tomorrow when we are going to discuss imaging. But this is how actually uh, uh, this is how I feel UV plane, by actually tracking it over a certain duration in the sky. And of course, the requirement is that the object that I'm tracking is actually not varying at all. It's like a steady source in the sky. And in that, so what this image, each of these panels is showing that the aperture which I have synthesized using large number of dishes, combining signals in pair, and tracking object over a certain duration of the sky. So you can see that depending on uh, how I have filled my UV plane, it actually looks like pretty close to a field aperture in the inner regions. But and as I go outer, I have less and less measurements, so there are some holes. So although I have actually using these experiment or observations synthesize an aperture, it is not a perfect field aperture as we would have gotten with a parabolic reflector. Of course, that also had some imperfections with that, but in this case, we can see that there are some major holes sitting here, and that leads to some very interesting applications of image processing. And those are the things we are going to discuss tomorrow, that how we take a measurements like this and reconstruct images which are as beautiful as you would see in any other wavelength domain. So this is my last slide. This brings to just summarizes what we have been talking about interferometry here, that instead of a single dish, we are using a large number of smaller antennas, and when we combine their I have this is a mistake here. We are not adding signals in pair, we are multiplying them. So yes, those who are if you are listening carefully would know that this is not accurate. So electronically, to sample the aperture EM field distribution, and this is what is called aperture synthesis achieved by Earth's rotation. And to physically, actually, to practically realize it, this was done by Martin Ryle. He played a very key role in this, and he was awarded a Nobel Prize in physics for practical applications of this technique in 1974. So this is the high point at which I would like to end. This is my summary slide for today. And these are some of the references you can refer to if you want to look at Fourier transform. You can look at any of your favorite books, but I would recommend you can, if you have a lot of time and also want to go really deep into it, you look at Bracewell. And then if you want to understand more of interferometry and synthesis, you can look at a book by Thomson, Moron, and Swenson. You can look at a lecture series by Anna Rao. It's titled Synthesis Imaging in Radio Astronomy, and lectures from these actually are available online. They're free. And then if you want to understand more about optics, and that's something I think very, very exciting and interesting, you can look at the book by Born and Wolf. And if you are starting at a slightly undergrad level, you can start with Jenkins and White first, and then go to Born and Wolf. But things like Van-Sitter's Wernicke theorem are discussed only in Born and Wolf. But one can understand only these if one understands basic properties of diffraction and interference. So I will end now with a quick note that tomorrow we are going to now talk about calibration and imaging, and how some of these things are tackled with modern radio interferometers. That's it for now. Thank you. So now we are going to take some questions. I have stopped sharing my slide. So like in the previous lecture, I'll first go to chat window. So I have stopped sharing. I'm going to, so first few minutes, I will take some questions from the chat window. So this first question is very good. This is what I was trying to elaborate in my last few slides, that the aperture that we have synthesized using an interferometer corresponds to discontinuous dish. It is not continuous. So we are going to understand this tomorrow, that how we tackle these discontinuities in image processing. I will come to that tomorrow. In very short, what we can do is that we can weight data in a certain ways to downweight the effect of those discontinuities. Because one of the major discontinuity that you are familiar with is, like, if you take a uniformly filled aperture, then it sort of ends abruptly at the edges, right? And that leads to rapid ringing. So what we can do to take to remove those remove the effect of that is to sort of taper my response close to edges. So there are simple signal processing techniques like that which we can apply and understand very easily using simple ideas of Fourier transform. make nice images, even though my dish is discontinuous. Now, the second question is from Rajat. Does the characteristics of an antenna remain the same for different types of antenna, that is dish and bow tie? Of course not, because even if I change a small thing like, let's say, the size of the aperture, its response is going to change. And you can see, like, just from the Fourier transform pairs, that if I take a rectangular aperture or circular aperture, the responses are going to be so different, right? It's not just that their main beam width going to be different, the side lobes are going to be different, and those are the details that matter a lot when we are going to make very sensitive measurements. Okay, so next we go to Google Doc. Okay, so Prince Sharma, if dishes direct the incoming radio waves towards the feed, how can we image the sources? Like CCDs, are dishes also position sensitive for the incoming photon? Okay, so I think we need to visualize it slightly differently. I'm understanding the question, but so directivity here is coming. So if I have a circular parabolic reflector, it's not receiving radiation from the entire sky. It has a certain response. So it is, most of the radiation is coming from the main lobe, right? So and then I have a detector placed there, which is going to collect, which will also have a power pattern. So it will, and I will adjust that power pattern such that it will illuminate a certain portion of the dish. And when so I will be collecting radiation from there, and that's how, and then I will take that signal and that voltage measurement. And if in this case, in the case of interferometry, I will be multiplying it with other antenna signals, and then I will be taking a Fourier transform to get the image. That's how it would work in this case. In case of so in optical domain, what happens that there's a Fourier transform that is taken by the lens, right? In case of radio interferometry, we don't have a lens like that in the same sense, like my eyes has a lens, like it is doing a Fourier transform when it is making an image. But in case of radio telescopes, we don't have a material like that. So the second Fourier transform that is to be done, which is done by lens, is actually done electronically in this case. How do we determine a particular wavelength to form an image? Is it based on trial and error method? No, not at all. It is based on two things. First thing is that understanding of physics. So let's say if I want to observe a star or an AGN, in case of star, I know it's a black body. In case of an AGN, I know that it has a certain broadband spectrum. So, and depending on what physical process I want to understand from that object, I will decide, okay, this is where I want to observe. In case I want to observe certain molecule or a certain atom spectral lines, then I know their rest frame wavelengths, and I can know at what redshift they are. Then I can tune my telescope to study their lines with that. So we choose at what wavelength to study based on physics. Okay, these were the selected questions. Okay, I think, and I'm also exceeding my time by now 3 minutes, so we can stop here. And I would like to thank everyone for joining today. And we will continue this discussion more from the imaging perspective in the next.